the ones that crush cabins.
This meeting is now being recorded.
And so in Yosemite Valley, the recent report has been published, it's about 2014, documenting the rockfalls, and they do this every so often. And in that report, they've documented 900 rockfalls between 1857 to 2012. And most of those rockfalls actually were documented more recently. They didn't have such a great recording system early on, but more recently, they're seeing 30 to 50 rockfalls per year in the valley. So it happens a lot. In that time, we know of 15 fatalities and at least 80 injuries. And so it is actually an issue in the valley. All right, so another thing about rockfalls is where are they happening in Yosemite Valley? And a quick glance at this map shows that they're kind of happening everywhere. And you might note that it does seem like there's a few more rockfalls happening around Yosemite Falls, Glacier Point, Royal Arches. And this is not because there are more rockfalls in those areas. It's actually because there's more people in those areas. So there's more people to notice the rockfalls and report them. And the other thing about this map is that you can see that the rockfalls are happening all throughout the year. They're happening in all seasons and all locations. And so, there is some seasonality. There is some triggering associated with rain and snow, but that's not where 100% of the rockfalls are coming from. So here we go. They're happening during all seasons, and we're getting maybe one rockfall per week, maybe less during a drought. So there is a little bit of rainfall triggering that goes on. So here's what the project was. We took some instruments, seismic instruments and acoustic instruments in the second year, and went out there in the winter and put some instruments on the formation known as Middle Brother. Middle Brother is a south-facing rock cliff, so that means that it snows, it rains, but then it melts and it dries out, and so we can actually get up there in the wintertime. The cliffs that are north-facing, they're covered in snow, they're covered in ice, they avalanche, they're very, very hazardous in the wintertime, so there's no real option to do any monitoring on the north-facing slopes. So we went out there on the south-facing slope, and Middle Brother also has a history of wintertime rockfalls, and so we thought maybe there would be a good chance of catching something. And so this is the Middle Brother formation, the three brothers. You can see that I have three rockfall source areas kind of lined out for you. I call them A, B, and C. A is a pretty large source area. It was actually the place where the largest rockfall that was ever recorded in Yosemite came from. 600,000 meter cube rockfall came down in the mid to late 80s and hit the road and closed it. So a pretty active area. And the instruments that we put out, we actually were able to access a ledge nearby to put instruments we thought were getting up a little bit closer to the rockfalls. And so that's where some of the stations were. The first year we only had one station with two instruments. The second year we had all three locations in operation, and one was on the ground. And so the question is, how do you find rockfalls in the seismic record? I put these instruments out. I didn't know what I was looking for because we didn't have any data. And so I just turned them on and let the instruments run. So there was continuous non-triggered recording that went on for several months. And so the first thing I did was set up a triggering algorithm. And I was lucky. There were some rockfalls that happened early on that helped me understand what a rockfall in the seismic record might look like. And I'll get to that in a little bit later. But there was also a lot of other things that went on. As you can see, you've got some examples in the bottom. These are spectrograms. And on the x-axis, you have time in seconds. And so the one on the left is 0 to 90 seconds. The one on the right is 0 to 120 seconds, so 2 minutes of data. And on the y-axis are frequency, the frequencies that are basically happening during these events. And so using the sort of the time versus frequency spectrogram, I can sort of see unique kind of signatures of different types of events. And you can see there's some rain on the left. These are, very short duration, somewhat high frequency spikes that are happening, frequently. That's a rain event. There's also a low frequency event at about 20 seconds. I'm not sure what that is. That might be a tree rocking nearby. That kind of thing happened when it was a bit windy. And on the right is an earthquake. These instruments were out. They're going to record earthquakes, and you can see the distinctive P wave arrival coming in at 20 seconds and then an S wave coming in at, say, 55 seconds. And so you see those dual arrivals of an earthquake, and And you can see the earthquake is also, lighting up, around 5 hertz, as opposed to the rain, which had a lot of energy at, 60 or 80 hertz, very different sorts of frequencies. And so that was part of how we were able to distinguish different types of events. And this was important because the triggering algorithm that I had recorded 66,000 triggers, and that's obviously too many to look at individually. But 1,300 of those triggers occurred at more than one location. So those were high probability real events as opposed to something like a tree rocking or a raindrop hitting my instrument. And there were 300 earthquakes in the record. And we know that because I was able to match the triggers that I had in the time with the earthquake catalog in California and eliminate those events. And I did spot check some of those events to confirm that they were indeed earthquakes. But, we were able to get rid of 300 events as earthquakes, and so there were 1,000 triggers at more than one location left that we took a closer look at. And there were 60 events that triggered at 4 or more stations. So that's kind of where we started, is by looking at those events that were triggering at lots and lots of stations, and then sort of going down to events that triggered at fewer stations, maybe at times when it was known to be quiet and not raining, that sort of thing. Definitely checked a lot of events. So here's some more examples of some of the noise that was triggering. You can see sort of resonant frequency bands that are steady on the top left. That's some sort of engine noise. There was some road construction going on below my instruments that winter. And again, you can see on the top right, there's this sort of regular weird spike going on in the bottom. That's definitely some sort of human-induced engine noise or something. I'm not exactly sure. On the bottom left, I was up there on a windy day collecting data. You can see the wind bands making the instruments noisy, and a rock fell. And maybe you noted in the first picture of me that I was wearing a helmet. This is why. But it was maybe a baseball-sized rock. It probably got blown off a ledge that was maybe 20 feet above me, not far, and landed behind me and scared me. And you can see that rock, that small rock landing very close, has a lot of energy in a very high frequency band. It looks like the numbers are cut off, but that's around 200 hertz. So very, very high band. It doesn't even look very similar to rain, but it's sort of similar. And of course, there's some rain that's a little bit less energetic than the rock on the bottom right. So this is some of the noise that was in the records that were not rock falls. And so I think this is a little out of order, but I'm going to skip this one. Sorry. We also had infrasound sensors out the second year, and so some of the other events that came through were, you can see on the top there, there are these weird little spikes going on, and I noticed this on Saturday mornings, and on more than one Saturday morning, and I just didn't, and this, by the way, this instrument was located in Yosemite Village. This instrument was in Greg Stock's backyard. And I finally asked him, I said, when does the garbage truck come around? And it turns out they come around on Saturday morning. And so you can see these are infrasound sensors. That's 20 to 200 hertz, so it's pretty low. You might be able to hear that if you have really good hearing, but probably not. And then the other thing that the infrasound, this is again not seismic, these are pressure waves coming through. On the bottom left is I looked at some of the records from the infrasound, in the spring, and it was very, very noisy in the low frequency bands, and that's probably Yosemite Falls. And I was able to take 2 of those instruments and do what we call cross correlation, where you take the waveforms and you match them to see how similar they are, and you can match them and see if they're similar with slightly different times, and that sort of time difference can tell you what direction the seismic waves, the acoustic waves are coming from, and how fast they're moving. And in the case of sound waves, we know what the speed of sound is. But there were also large pressure changes that were similar with 2 different instruments over time that were not moving at the speed of sound. They were going much, much slower. And that might be wind. I'm thinking these are sort of barometric pressure wind gusts that the acoustic sensors are picking up. So I guess this is what this one was, is that you can see the wavefront coming in. It goes to sensor number 1. It continues to travel. It lights up sensor number 2, and then sensor number 3. And you know something about the distances of the sensors from each other, and you know what the timing is, and you know what the speed of sound is. And so using those sorts of a little bit of geometry, you can back out the direction of the wavefront that's coming in. So that's how we were able to sort of figure out where stuff was coming from and how fast it was moving. And so, so besides all this noisy stuff that happened, we actually did have some rockfalls, which is what's interesting in this talk. And I got really lucky. 1 week after I put the instruments out, there was a rockfall from Middle Brother, which is very close to where the instruments were, maybe 500 meters away. And this came from source area B. So there were those 3 source areas. This one came from source area B. I know the release point because there were subsequent rockfalls where people saw rocks coming out of that area, and that area did have a fresh scar. And you can see that, a boulder, there's a boulder that's on the road. That was the largest chunk that we were able to identify, and it's sitting on the road. This is the road that everybody drives on when they go in and out of the valley, or rather out of the valley. And so, this was interesting because it didn't hit anybody or cause any problems, but it did, impact infrastructure. And you can see that it also sort of decapitated a tree down below on its way to the road. And there were other fragments as well on the road. It was not a single boulder. It broke into a million pieces, and there were little fragments all over the place. And so a little bit about the weather. You can sort of see the weather leading up to the time. Those red and blue spikes are temperature, and you can see in the days before the rockfall you had sun, so you see some warm temperatures during the day and then cooler at night. And you see that for a couple of days, and then it starts to snow and the temperature stabilizes, and this is because you don't have the thermal heating that you see during the day with the sun. And so it did start to rain, and so this rockfall was associated with precipitation. And I had 2 instruments out. This was the first year I was running it. I only had 2 instruments, 1 single station, an accelerometer and a geophone. Each of those had 3 sensors on them, 1 in the X, Y, and Z direction. And so that's 6 total records that you can see. And they're pretty consistent with each other. And again, I looked at a spectrogram. And so again, on the bottom, you have 0 to 90 seconds, about a minute and a half, and the frequency is 0 to 200 hertz. And you can see these, the geophone is on the left, and you can see sort of low frequencies with the occasional big spike that comes in. And there's a little bit of noise early on. You can see it's a little bit quiet. You have sort of small something happening on maybe 27 seconds in that record on the top, and then it really gets big, a little bit after 30 seconds. And so there's 6 or 7 or 8 seconds of sort of activity that occurs before you really get a big impact. And so that's a pretty typical signature of a rockfall. And here we go. Because there was this rockfall, this is the first one is on the upper left. That's the rockfall that was the big one that people saw, and the big one being that boulder that I was standing next to. But in addition to that, there were some afterfalls, sort of like aftershocks. And some of these were witnessed. And so I know that they were rockfalls because I know that somebody was there who recorded the time, who told me that there was a rockfall. And so I have confirmation that on January 4th, that was definitely a rockfall. On January 8th, on the upper right-hand corner, this was witnessed by Greg Stock, so he's a highly reliable witness. And I'm not sure that I would have known for sure that that event was a rockfall because it's pretty weak. It's very little going on, but he saw it. It happened. This is what the seismic record recorded at the same time that he was there. And so I'm fairly confident that that's a rockfall. And then in addition to the initial event on this 18th of December, people sort of reported that additional rockfalls came down. They didn't really say what time exactly they were, but they were saying that there were additional rockfalls happening. And so I don't know exactly when those were, but I did find these events in the seismic record, and so I think these are the events that were happening that people saw. And then in the sort of middle center was another event that nobody saw because it happened in the middle of the night. And but it looks very similar in character to some of these other events. And so even though nobody saw this happen, I think that there was a rockfall that happened on the 28th of February that probably came from the same area based on the way it looks with these sort of individual spikes, the frequencies, they go from 0 to maybe 140, 150 hertz. And so it's very similar. And the other thing about these frequencies that is important to note is that higher frequencies will attenuate with distance. And so rockfalls that are far away will not have as many high frequency spikes as rockfalls that are very, very close. And so the frequency that you see in these rockfalls is a clue as to how close it might be. And on this next slide, I'll sort of expand on that. And in A, the top left corner, is the Awea Point rockfall. This was 6.5 kilometers away, very far away compared to everything else, which was 300, 400, maybe 800 meters at the farthest. And the Awea Point rockfall was the largest rockfall in 20 years in Yosemite National Park. So it's a very large event, 45,000 cubic meters, as opposed to the other events, which are probably less than 5 cubic meters. And you can see with the Awea Point event, we really don't have much energy, above, say, 20 hertz. There's a little bit, but not a lot. Versus the events that are very close, you're seeing energy in the frequency band way above 200 hertz. And so you can sort of see the clue. B was, again, the second farthest event. This was a rockfall that was heard by a guide in the park, not seen. And we were able to identify the direction the waves were coming from based on the spacing of the sensors. And so we know that this event was coming from the west of my instruments. And this was the event, and you can see that it sort of tops out around 120 hertz. The others are from other Middle Brother source areas. In one case, event D, I know that this was a rockfall. Nobody saw this rockfall. It happened at 9:33 p.m. But I had my infrasound sensors out on the cliff below the Middle Brother A source area for a while. They had a long cable, and they were out there for about a month. And when I went to check on the data, I discovered that some rocks had actually hit the cable and damaged it. And so I basically decided not to have my instruments out there after that. But I was able to, because there was a damaged cable, pinpoint exactly when the rockfall happened, because that's when the data stopped for that particular sensor. There were other sensors, the seismic sensors, that were still in operation and did record this rockfall. And so I know that this is a rockfall because my instruments got hit. I've got some physical evidence. And then the other events here, C and E, were not reported. They both happened at night, 2:24 a.m., 9:21 a.m. And I think that C came from Middle Brother A source area because of its frequency response. Looks like a decent-sized rockfall. And, event E, I'm not really sure where it came from, but it probably was a little bit farther away than C because its frequency response is a little bit lower. And then finally in the bottom, F, is a very odd event because this happened the very next day from the December 18th event that I showed you previously. And so at first we thought it was an afterfall from that same series. But there was a witness, this is a search and rescue person, I believe, who saw it happen, who said, no, it happened from this other area that's different. And when we looked at the seismic record, it does look different than the other ones. As you can see, they all have multiple strikes. Basically, the rocks are coming out, and they're impacting the cliff multiple times on the way down to the talus, versus this event F. It only looks like a single impact, and it does have a little bit of stuff happening early, around 20 seconds, but then it goes really quiet. And that looks to me like the rockfall went ballistic. It basically let loose, and it went ballistic, and then it impacted the talus with one big strike, which is different than the other event. And so based on its character and based on the eyewitness reliability, I think that maybe there was a second rockfall in the vicinity that came from a different area. So that gives you an idea of what sorts of things that we were recording, and some of them were rockfalls that nobody saw and we wouldn't have known about had we not had seismic instrumentation out there. So now I'm going to talk about Awea Point. So this graph shows 0 to 150 kilometers. There's several seismic sensors. These are mostly strong motion earthquake sensors that are run. There was what they said was a magnitude 2.4 earthquake centered in Yosemite National Park. And the top sensor at 0 kilometers, that's my instrument. And so you can see a very distinct sort of a weak event followed by a strong impact that happens later. And so this happened at 5:30 in the morning, and basically nobody saw or heard this, actually, even though it was a really big rockfall. But it turns out that Greg Stock was kind of handed this seismic event at 8 in the morning. He was giving a talk, and he went out later on that morning to have a look, and sure enough, there was a rockfall. And so you can see Half Dome, and then you can see a point just below Half Dome. This is called Awea Point, And you can see this is the track of the rock fall. This is actually about 2,000 feet. It went from top to bottom. So it's a very big event. At the bottom you can see there's a bunch of new talus, and there was the Mirror Lake Trail. The loop trail actually goes right through that area, and so that new talus covered about 300 meters of that trail. So a pretty significant event. And so one of the things that we also have is we had climbers who were out climbing across from this event who witnessed it. Nobody in the village witnessed it, but some climbers did. So here's what one of them has to say. It first woke me up while sleeping on dinner ledge, early morning hours. The first time it woke me up, it was a pretty large fall coming down the side. The sparks at the lead end of the dust cloud really blew me away. This process went on for what seemed like all night. Then at the pre-dawn hours, I woke to a huge cannon boom, a sound, jerked up, looked over to see the entire side of a Wea Point shrouded in a massive dust cloud falling down. The lead end looked like a massive fireworks show. When it slammed into the floor, it crashed down into a huge plume of dust that went upwards and pushed out all the way across the valley floor. So there's a couple things that are really interesting about this eyewitness account. One is there were sparks coming down, which is what John Muir said that he saw, so that's pretty neat. And the other thing that's probably more important is that the main event happened after many, many hours of precursory rock falls. So there were several hours of little rock falls happening that were loud enough to wake him up and annoy him, and that preceded this big event. So that's very, very interesting. On the right is a photograph that another climber took. This is not the main event. This is actually an after fall. This is the rock fall that happened the next day. And so not only were there precursory rock falls, but there were rock falls happening after the main event. So very active, so sort of a pattern of activity there. That's interesting. And here's another shot of the rock fall. And you can see that because of this rock fall, they did have to close this trail, and they had it closed for a couple of years, maybe 3 or 4 years, because they were concerned about the stability, the continuing instability of the event. And you can also see that you have these dust clouds that go beyond where the rocks end up. They go all the way across the valley where the rocks stop, sort of in that talus pile. Okay, so what do we get from that? We've got we had infrasound and we had geophones, and of course accelerometers, but the geophones tended to have better records. You can see 0 to 40 hertz on the left. That's the geophone, so lower frequency than some of those closer events. But you can sort of see an event that comes in at about maybe 5 seconds, and then a big boom at about 15 seconds. So there's about 9 or 10 seconds of sort of quiet rockfall activity, which then when the rocks hit something really big, you see a big impact. And the infrasound also sees that sort of thing. You see a little bit of disturbance that's happening a few seconds before, and then you sort of see the big disturbance that happens afterward. And so where were these instruments located? A Wea Point, you can see the star on the right, and the instruments are the yellow triangles. And most of them were at the Three Brothers, but I also happened to have a station that was in Yosemite Village. The Three Brothers instruments were on granite. They were on rock, and in the village they're located on some sort of fill. So sort of different coupling to the geology in those areas. And the infrasound was also in the village. And so some of the other things that we had for this rockfall event were Greg Stock at Yosemite National Park had commissioned a lot of high-resolution photography called the Yosemite X-Res Project. And if those of you are on your computer, you can go and you can Google Yosemite X-Res, and you can get to a website that's run by, I think, Silverlight. And you can actually zoom into the cliffs at different locations, and you can zoom in and out, and you can see rock climbers. It's a really neat project that went on. But one of its uses is also to look at sort of the before and after of a rockfall. So here's the before shot from Yosemite X-Res. And I went out and hiked out to the diving board on the side, near the side of Half Dome, a very famous spot for photography, and took an after shot. So I'll do that again. There's the before, and there's the after. So we can see exactly what broke loose and how big it was, what shape it was, just from photography. So that's really neat. All right. The other thing that we had was LIDAR. There was a LIDAR survey flown in 2006 that was aerial over the park, And then after this rockfall, I got a grant from the National Center for Airborne Laser Mapping to have it flown in that area again. So we had a post-rockfall LiDAR, and then Brian Collins came out with his terrestrial LiDAR system and did some terrestrial LiDAR scanning. And so there we have a pretty good data set of the three different LiDAR scans, so that we was able to back out some of the geometry of this rockfall. And just a quick comparison, there's the LiDAR on the left, there's what the rockfall looks like on the right, and you can see how similar they look, similar locations.
Sorry, am I a little longer?
Yeah, was that you on the phone with Sonia?
Huh?
Was that you on the phone with Sonia?
We can hear people talking. Hello.
We're just putting together a response for her right now.
Might want to mute yourself.
Call Bill and Tim first.
Hello,
Okay.
we have someone in the background talking. Can you push *6 and mute yourself, please? Thank you.
There we go. Thank you. All right. So using this LiDAR, this is again Brian Collins did most of this work. You can see A is a photograph of the block that detached before it detached. B is a LiDAR version of that, and you can see it's a pretty big block. It's about 50 meters across. It's 26 meters at its widest point. It's a big piece of rock, and here's the corresponding seismic record. We can see at D1, 56.5 seconds, or 56 and a little bit of seconds. So you can start to see a little bit of activity on the seismic. Followed by D2, something happens, it gets a little bit noisier, followed by the main impact at about 66 seconds. So there's really distinct phases that are happening during this rockfall that we were picking up seismically. And so what can we do with that? Oh, and by the way, the rock, just so you have an idea, was about the same size and height as the Statue of Liberty. And so we did a little ballistic analysis about, it might have slid out on a ledge and how much friction would be required to get a certain acceleration, and did a little bit of analysis on the timing of that ballistic analysis to sort of match that up with some of the seismic record. Given the LiDAR also allowed us to see where the rockfall had impacted the cliff on the way down. So we knew exactly where there were little bits of rocks missing on the way down that would have gotten hit, and we sort of knew also where there was no rock missing, and so the rock mass must have been traveling ballistically through the air at that point in time. And we were able to sort of back out that D1 kind of corresponds to the block starting to slide, and D2 is the rock basically going ballistic in little chunks raining down, but the big impact happened at D3. There's a look at the ballistic analysis. You can see the initial source area, 25,000 meter cubed. It went about 130 meters ballistically. It impacted the cliff, knocked a few more rocks out, and then continued to travel down and hit a big ledge and knocked out basically a ledge that was almost the same size as the initial rockfall. The other thing that the LiDAR was able to sort of back out was that there was talus. There were changes to the talus. You can see the pre- and post-talus surface. And I'll get into that if I've got time. Here's the mid-cliff impact. That's what the ledge looks like before the rock hits it. This is kind of what it looked like afterward. And so you can see there's a pretty big amount of rock and trees missing from this ledge. So again, it induced further rock falls.
There are the trees. Okay, now I've got the scale. All right.
Yeah, sorry, I can go back on that for those who see some trees. There's a big pine tree on the right-hand side you can see, and then the rest are sort of smaller oaks. And then the pine tree's still there, but a lot of the rocks and oaks are gone. And the point at which that cliff went from 70 degrees, the point at which the rocks hit that cliff is when the slope changed from 70 degrees to 35 degrees. And so that rock slammed into that ledge at about 73 meters per second, or 160 miles per hour, and knocked out the entire ledge. Okay. I've got a little bit of feedback. Can you guys please mute your phones? Okay. And so this impact in the mid cliff ledge is what caused the magnitude 2.4 earthquake. It wasn't really an earthquake, right? It's a rockfall impacting a cliff that makes a seismic signal that the computers thought was an earthquake, but that's what caused that event to be recorded. After it impacted that ledge, it traveled another 300 meters down the cliff for about 1,000 feet, and lots of impacts on the way down. And while it's traveling down, it's also sort of pushing an air mass in front of it. You have this massive rock that's traveling pretty fast, and it's also pushing the air in front of it. And when it hits the ground, the air doesn't have anywhere to go, and so the air sort of shoots out at extremely high speed, sort of like you've turned the water into a hose, and that air blast is enough to knock trees down by itself. And this is a phenomenon that has been seen before. This was a phenomenon that was seen in 1996 at Happy Isles. And this rockfall at Weah Point and the one at Happy Isles are about the same size. Weah Point is actually a little bit bigger. But you can sort of see these little trees beyond the talus that are laying down. And I walked around down there, and there's no boulders. These trees were not hit by boulders. They were simply knocked over by a wind blast. And so that's a pretty significant effect. And that's kind of what it looks like on the ground below the talus. And you can see all this new talus. This is, in fact, the area where the trail went right through. And again, this rockfall happened at 5:30 in the morning, so thank goodness. Had it happened in the afternoon, we might have seen somebody get hurt. And so very fortunate that this happened at the time it did happen, because you can see there's quite a lot of destruction, new rocks that are in this area. And so the air blast is sort of interesting, because that's the sort of thing that I would expect to see on the infrasound acoustic. And so, first of all, I only had 2 acoustic sensors out at the time that were operational when this happened. The red and the blue, you can see that the signals track each other really well for about 20 seconds. And when you zoom in over 1 second, you can see a definite separation in the arrivals of the wave coming through. And so this lets us back out sort of the direction of the rockfall. And when we did this, because we've only got 2, you actually need 4 sensors to get a 3-dimensional location pinpointed. With 2, I could sort of come up with a cone of possibilities, if you will. And that rockfall is definitely within that cone. So you can see that's what the acoustic sensors were coming up with. But in addition to that, we talked about that D1, that D2, and that impact signal that we saw in the seismic, and we're seeing sort of similar patterns in the infrasound acoustic. You can sort of see I don't really see D1. It's kind of lost in the noise, but I do see the D2, which is when the rocks kind of start going ballistic and sort of smacking the cliffs. And then you see that big impact come in. And when I filtered it for low frequency, you see a definite change at about 22 seconds. You see sort of the waves are kind of bouncing around in a sort of normal wave, sine wave kind of way, and then you see a definite change in slope with this big event coming through. And I think that's the air blast. So I think the infrasound is definitely picking up that air blast signal. So that's just kind of interesting. And then the last thing that, again, this is Brian Collins noticed this with his LiDAR analysis, where he was able to map out the before and after talus surface, and before it's covered in trees as well. And the green is before and the blue is after. And what you can see is that the rocks slammed into the talus with such force that they actually were able to push the talus down slope. And the final slope angle of that talus is actually less than the initial. And so that was kind of surprising. The talus slope is less steep after a large energetic rockfall impact. And the question is that typical? Is that something that normally happens? Or are steeper slopes maybe more indicative of smaller events that happen, lots and lots of small events versus one big event? And I don't think we really know. But 7,000 meter cube of talus was remobilized in this event. So in addition to the new rocks, 7,000 meter cube of talus moved as well. And because we had such good data on before and after, we know what the volume of the rockfall was. We know it was 46,700 meter cubed, and we know what the volume of the talus was that was there before and after. And based on that, Brian was able to calculate a talus porosity, which ended up being 14%. And this is lower than what has been published previously in the literature. So again, that was a bit of a surprising result. But then again, maybe not. This was a very energetic rockfall. The rocks got smashed into lots and lots of little pieces. If you stand at the bottom of this rockfall, you don't really see a lot of big boulders. You see sort of small boulders and a lot of little boulders, and there was a lot of dust. And so maybe a low porosity rockfall makes sense because you had all these little pieces that were filling in the gaps between the big pieces. But that was another interesting kind of result that came out of this. All right. So those were some of the results that we're able to do. I'm almost out of time here, but just sort of this is the last shot I have here. This is a photograph that was taken on top of a WIA point by somebody who climbed up there just for fun. And you can look back and you can see the line of sight to where the instruments were. You can see that the infrasound is actually behind Washington Column in the village, and you can see the brothers are sort of a direct line of sight, but they're on the other side of the valley. You can see where my instruments were, so you get an idea of how these things were set up spatially. And so that's basically all I have for that, just to kind of show you some of the stuff that we did and found out, that we were able to find rockfalls that we didn't know about, that there were some, at least at Middle Brother, we were able to record rockfalls that were happening after the main event, if you will. At a WIA point, we did not get any of those pre and post rockfalls, and I think it's because we were just too far away. 6.5 kilometers isn't close enough for the seismic to really pick up those smaller rockfalls, but it definitely picked up the big ones. And so I had a lot of help from a lot of people, including Bob, who is the next speaker, and had a lot of people that helped carry instruments up and down the cliffs. And I guess I want to thank all these folks and just acknowledge that I did not do this alone. And I think that's all I've got for now.
All right. Thank you, Valerie. Now, do we have any questions for Valerie? I'm looking at my board here. I don't have anything under the Q&A. So if you have any questions, send it in right now, and we'll. You've got Valerie on the line. She can answer it directly.
Did she want to say anything about the sparks or the fire from the falls?
That's just kind of, I think it's just friction. I think it's the spirit. It was one of those things that I thought was really interesting when I read John Muir's account, and then I read the account from the climbers who were up there, that they both were sort of astonished at the sparks that were flying through the air, the heat that was generated. One of the things that, I'd like to, was just interested in doing at one point was backing out some of the energy, like how much energy, do you have, how much energy goes into the generating seismic waves? And the answer is not very much. It's like 1,000th of the kinetic energy that's coming down goes into seismic waves. And so, I started wondering about where's all the energy going? Is it going to breaking up the rocks? Is it going to generating heat? I don't know. And so I just thought that was an interesting thing. But I don't have much to say about it other than cool. It's really neat. Are there any other questions?
Oh, I've got some questions up on my board now. Let's take a look.
People can email me their questions if they'd like.
Okay, is the park going to use this information to somehow improve safety in the park?
That's a good question. The park has taken more of an administrative control approach to rockfalls. I don't think that we can predict rockfalls per se. I think it might be possible to predict some of the rockfalls using methods that I didn't really show you today. I would like to do more research on some of the acoustic monitoring, because there have been lots of reports of cracking noises and precursory rockfalls that people can hear, and if people can hear them, then instruments should be able to record them. But having said that, there's a lot of rockfalls that happen with no indication that anything was going to happen ahead of time. And so I don't think prediction of rockfalls is really the way to go in the long run. And so what the park has done in the past 10 years is they've sort of zoned off areas of the park as areas that are highly susceptible to rockfalls and areas that are less susceptible. Greg Stock should be the one talking about this, but he went out and counted all the boulders that rolled beyond the talus slopes and found about 500 of them, and sort of drew a 90% line. Like 90% of the boulders are within this line and 10% are outside. And so that activity, that report that came out, I think 5 or 6 years ago, is how they are now planning their infrastructure and deciding which infrastructure to close. Curry Village, one of the unique things about Curry Village is it sort of just got built willy-nilly over the past 80 years or 100 years, and some of those cabins were actually kind of in the talus. And, there was no geologist working in the park for a long, long time. And so, you guys are geologists. You know that maybe building in talus isn't the best idea. But, nobody really knew that when they were building these cabins. And because of some of the work that has gone on in the last 10, 15 years, they were able to make a really good argument for closing some of these cabins to improve public safety. And so are they using work I'm doing? Not really. But there's a lot of interesting rockfall research that is going on in the park that is sort of helping them do better planning for the future.
Okay.
Obviously, okay, keep going.
Yeah, we have a couple more questions. One from Jack Tung. And are there differences in the observed signals from rocks that fall on fill material compared with rocks that fall on something more solid, like more solid rock?
That's a good question. I think the answer is probably yes, but what I'm seeing is mostly rock that's impacting the cliff and the talus. And so mostly what I'm seeing is rocks that are impacting other rocks. There have been some similar efforts in Europe where they have more rock slides. And I think the answer is, yeah, there are slight differences in what you're seeing. But Yosemite's pretty unique. It's very steep. We have a lot of ballistic rock falls, which is unusual in the landslide world. Most landslides are not going ballistic. And we're seeing these really high energy impacts. And I would expect that to be very, very different for a sort of a landslide or a rock slide. Or even hitting softer materials. I would expect that to be a little bit different.
Okay, we have a question from Jason. He says, the base of Oahe pre-fall mass looks highly fractured. Could this have produced the finer material and low porosity of the talus?
The base looks highly fractured. I'm not really sure I understand that. The base of it was already a talus slope. And so, yeah, you had a lot of big boulders. Some of the things we've noticed on talus slopes is that a lot of times big boulders are up near the top. And so could that have impacted the low porosity? Maybe. I'm not sure that I think that what I'm comparing the low porosity to is other talus slopes. Other geomorphologists have gone out and tried to estimate talus porosity, and then we did a talus porosity estimate and came up with a very different number. And I'm not sure what that really means, but it was interesting. I'm not sure if that answered the question, though.
Okay. And Department of Water Resources Northern Region has a question of whether you have any data on how many climbers are injured from rock falls.
There is some data. I think that they do keep a tally of known people that get hurt by rock falls, but I don't think it's a huge number. Certainly there have been some events, and there's an awful lot of events where you have very small, basketball-sized rocks that come down that, scare somebody. But I don't think it's a huge number off the top of my head. But there are usually, there's definitely been a few events, a few instances of rockfall scares in the last couple of years. I think there was a big chunk of Half Dome that came off on the most popular route for aid climbers. Nobody was up there, thank goodness. But had they been, they would have gotten hurt. And there's definitely been some events on El Cap that have gotten the attention of climbers in the recent years.
Okay.
All right.
Well, that's everything I have for questions. If you have any more questions, send them in. We'll get them to Valerie, and we'll get you the answers through your email. So if you do send in a question, include your email, because I don't think we have your email recorded from logging in. So do that. If you think of anything later, I know how it goes. Once you walk away, you think of the great question. So don't be afraid to get back in touch with us, and we'll get the question to Valerie and get the answer back to you. Well, thanks a lot, Valerie. It's very interesting. We appreciate you making your presentation today.
All right.
Okay, now our next presenter is Bob Sass. He's our second speaker today. He studied geology at James Madison University and San Francisco State University, and he's become a internationally qualified specialist in engineering geomorphology and terrain mapping for assessing landslide hazards. In 2010, he traveled to Hong Kong to help launch the airborne LiDAR applications to evaluate the natural terrain for landslide hazards. Based on his reputation and experience doing this, he was invited to be one of 6 technical reviewers of revising guidelines on landslide hazard studies for the Hong Kong government. He has recently joined AECOM's water group in Sacramento, where he's helping meet the growing needs of water infrastructure engineering and remote sensing for wildfire and geologic hazard management. Bob is going to be presenting on integrating GIS modeling and terrain mapping using airborne LiDAR for assessing landslide hazards. His study area is the work he did in Hong Kong. So good morning, Bob. Are you on the line?
Good morning. Yes, I'm here. Thank you.
Okay, and I see it looks like you have your presentation up.
Yep.
So welcome to Geology Symposium, and you can go ahead and get started.
Thank you very much. It's good to be here online, and also good to be back in California after 6 years overseas. So many engineering geologists will be familiar with conventional mapping and analytical approaches to landslide hazard assessment. Those approaches, mostly in the realm of terrain evaluation, have developed over some number of decades, especially since the 1960s. I won't be talking too much about those conventional approaches. I'll briefly gloss over the approach that we use in Hong Kong, and more I'll be focused on discussing an approach that is unique and non-conventional, using remote sensing and GIS. So Hong Kong, as you can see from this photograph, is a spectacular mix of urban, mountainous, and coastal landscapes. It has these steep, tropically weathered mountainsides that directly abut a very developed urban environment. And because of its subtropical location along the South China Sea, it has a humid climate. It's affected by monsoonal rainfall, and also affected by tropical cyclones and typhoons, or as they're known in the Atlantic, hurricanes. So I'll discuss a little bit more about the context of landslides and public safety in Hong Kong, and go over what are generally in the industry and government called NTHS, or natural terrain landslide hazard studies, and they differentiate the natural terrain studies from slope engineering studies for man-made slopes. And then I'll go into some airborne LiDAR, automated mapping, and integrated geotechnical GIS modeling approaches to landslide hazard assessment. So here's another good example of Hong Kong's steep vegetated terrain going directly into very dense high-rise structures. Hong Kong has the highest density of high-rise buildings in the world, 2 times as many as New York City, and a much smaller land area. Fewer people, but the urban density in the highest density areas is about 150,000 people per square mile. It's a pretty unimaginable environment to be in if you're used to being in most any city in California. So all of those essentially flat-lying or gently sloping areas along hillsides or in reclaimed lands abut about 230 square miles of natural terrain, and that's that vegetated hillside that you see there. To the lower left of this photograph in the background. And just for some context, this is a slope safety environment. The Hong Kong government, under the Geotechnical Engineering Office, spends nearly $50 million a year on slope safety and geotechnics. And there are several very large programs and many international consultants and local consultants and contractors to support this infrastructure development. Hong Kong is mostly granitic and volcanic rocks. It is considered tectonically stable, so there is no seismicity from the basement of basement rocks in Hong Kong. It's all tropically weathered. It's been affected by multiple significant sea level rises, being a coastal mountainous environment. So through those sea level rises, since the mid to late Pleistocene, there's a thick accumulation of colluvium, and that is also tropically weathered. And we have a maximum rainfall of about 120 inches per year. We usually get up to about 90 inches per year, and much of that rain falls within a 5-month period. So we get very high-intensity rainstorms in Hong Kong that typically trigger some number of landslides. The context for the natural terrain hazard studies is essentially set from a single day, the 18th of June, 1972. 148 people lost their lives. There were people from all parts of society. There were government officials that were killed, rich bankers that were killed. This landslide affected the most expensive piece of real estate in the world at the time. I think Abu Dhabi leads that number now. Anyway, still being the second most expensive piece of real estate in the world. And you can see that this landslide, called the Posandro landslide, resulted or initiated in essentially natural terrain, traveled down across a road embankment, then traveled down through the basement of a high-rise structure, completely collapsing that building, and then subsequently hitting another high-rise building down here, and you can see the partial collapse of that structure here. Between 60 and 70 people lost their lives in this event. And just across Hong Kong Harbor, on the other side in Kowloon, another landslide on the same day resulted in a similar number of deaths. About 70 people were inundated by this landslide, and this affected a squatter village, so this affects the poorest people of Hong Kong. So landslides and slope safety in Hong Kong affects everybody, and no one is immune to them, whether you live directly below a hillside or whether you travel via transportation infrastructure that's affected. These landslides continue today, and we can see that some debris flows can initiate as very small source volume landslides, less than 100 cubic meters in source volume, and then resulting in tens of thousands of cubic meters of debris as they travel down. There's over 10,000 shallow landslides that have been observed from aerial photographs since 1961. Over 2,400 of those occurred in 2008 in West Lantau. Lantau is a large, mostly unpopulated island, fortunately mostly unpopulated. However, this sort of event, looking at the climatology and weather systems in Hong Kong, could certainly occur over Hong Kong Island and occur above those very high-density urban areas. So there is certainly concern for this. A typical study area for a landslide hazard assessment in Hong Kong looks something like this. It's a variety of watersheds or catchments that are divvied up based on interfluves, and these usually affect some sort of infrastructure or proposed redevelopment. This is a bus depot that is proposed for redevelopment for 2 high-rise residential buildings. There are 2 basic phases to a natural terrain hazard study. That is the study itself in the investigation phase, and then the engineering construction phase for NTH, natural terrain hazard mitigation measures, design and construction. This essentially follows a typical process for an engineering or geoscience study, where we do a depth study of existing databases, aerial photographs, looking for landslides, and then also mapping the terrain from aerial photography. Perform a site investigation with intrusive ground investigations. In the lower right there, you can see the top of a trial pit. Those are excavated to 3 meters in depth, so they have to be shored. And there's also some drilling that goes on in these natural terrain studies, but typically it's shallow, not into strong rock. We also do extensive field mapping. You can see our field tracks for this relatively small study area of about half a square mile in an area. And then we do deploy GIS for this, but it's just for making maps. So we integrate the field mapping and the aerial photography-based mapping into a GIS map, and then present various engineering information, such as the laboratory test results for soils testing. And then we reformulate all of the field observations, all of the aerial photograph interpretations, and maybe looking at rock masses and those sorts of things for potential instabilities there into an engineering geological assessment. And that engineering geological assessment then informs the hazard assessment and hazard zonation. And in the right there, you can see the hazard zonation map. And that's just divvied up to show the type, volume, and extent of landslide hazards, but it doesn't necessarily convey the relative severity or the susceptibility of the terrain to future landslides. So there are some gaps in these types of studies. It can be very difficult to make a strong prediction for a site about its future potential for landslides as far as magnitude and frequency, but there are some approaches that can be used for doing that. And those will also feed back into some of the approaches I'll be presenting later. We do some modeling. This is relatively basic analytical modeling where you can even construct a spreadsheet to run these sorts of models where you're trying to measure the volume and distance and impact force of debris from a landslide or from rock impact from a falling rock or boulder. And then we go into the engineering phase, and typically the engineering phase almost always goes forward. It's a very conservative risk management practice in Hong Kong, and so we typically construct either flexible barriers in the image on the left or rigid barriers shown in the engineering schematic on the right. The main products that the engineering geologist will develop for a landslide study is a photo-interpreted geomorphological and terrain classification map. And essentially what each of these colored areas shows is a unit of terrain that has similar geological, hydrological, topographic, and geomorphological conditions. And so when you have a similarity of those types of conditions, it usually relates to similar magnitudes and types of landslide hazards. So that map, which is basically generated from photo interpretation, aerial photograph interpretation that is, can then be taken into the field and used as a base map to generate the Surficial geological map, which maps out the various land uses and also the types of colluvium, their relative ages, and then this is also informed by intrusive ground investigation. You can see for a site study, we do typically do very intensive ground investigation, and this is to build up the engineering geological model, the information-based model, not the computer model, so that we can really understand how this particular hillside fits into the greater context of Hong Kong. And that's really important for us to do in order to inform our judgment when we're making the hazard assessment. Because if it's not informed by geoscience, what is it informed by? It would just be engineering judgment. So we try to apply a bit of scientific judgment and assist the engineers downstream in understanding those judgments so that we can formulate a good mitigation strategy. Then those two previous maps are essentially assimilated and analyzed in order to come up with a landslide hazard zonation map. And each of these hazard zones conveys a particular volume of landslide. For this area, the volumes were on the order of 200 cubic meter source volume to 300 cubic meter source volume. And then you can see the schematic down here of the proposed residential buildings, and then the schematic for pretty extensive flexible and rigid barriers to be constructed around that. And a flexible barrier looks something like this, and a rigid barrier in design phase looks something like this. These are very thick concrete reinforced steel slab foundations, raking pile foundations. So what is airborne LiDAR, and why is it important to what I'm talking about? Well, essentially, I imagine most of you are probably familiar with LiDAR, but essentially it's laser scanning across the landscape to pick up various features, including the terrain beneath dense vegetation. It can be used for a variety of purposes. Forestry is a common application. Geoarchaeology, this is from an image from Belize, where all of this old archaeological finds are covered by dense tropical vegetation. It can also be used for infrastructure modeling, monitoring. And the sky's the limit. Discrete multi-return is kind of going out. We have full waveform and Geiger mode coming in, and we have this really wonderful emerging technology for latent guided spectroscopy that's becoming very important for forestry and wildfire applications in California in particular. So the technology's been rapidly improving. It's starting to integrate with other technologies, diversifying in a much faster pace than anything happening in photogrammetry, although UAVs and photogram are becoming hot topics for large area studies. So in 2011, Hong Kong collected its region-wide LiDAR survey, and that's the LiDAR data that I've been using. So why would we use LiDAR in Hong Kong? Well, it's because it reveals the terrain in a pretty complex environment. We can remove all of these buildings, we can remove all of this vegetation, and we can look at the geotechnical structures, engineered slopes, and we can also look at the natural ground. But it's also a good idea to use the LiDAR because it's in the revised technical guidelines. And truth be told, I wrote this part of the updated guidelines to basically put forward that it would be a good idea to start integrating GIS-enabled modeling with LiDAR for rapid regional assessments. So the approach to utilizing the LiDAR in the landslide hazard assessment in a more meaningful manner than just using it as a base topographic layer is to perform automated mapping on a LiDAR-generated digital elevation model, and then to utilize that same DEM for integrated geotechnical and GIS modeling. So there are field and lab data inputs that can be utilized. You don't have to have those for a regional study, but for a site study, you should have the field and soils laboratory testing data available. We also then basically running several algorithms across the DEM to generate a terrain classification map and a geomorphological map. And then the automated map and the geotechnical parameters are combined to form terrain units that then are associated with things like friction angle and cohesion, and those will vary across a landscape because the soils do vary. And then that becomes a soils geotechnical parameters map. And then that map and the LiDAR DEM, in order to derive slope angles, which are, of course, very important in calculating factor of safeties for landslides, those two layers are then integrated into a model called PISA-M. It's a slope stability model. It's similar to other models that you may be familiar with, like SHAO-STAB or SynMap. And then for a regional study, you may run it without the soils geotechnical parameters map, but for a site study, you would run it both without the soils parameters map and with the soils parameters map, and then you would calibrate the model using the soils parameter map. And then this essentially leads to a probability of failure map and a model post-audit. So sorry for this flow diagram and going through the text, but there'll be lots of pretty pictures coming up. It's really important that we observe the typical problem in modeling, which is bad data in and means bad data out. So it's very important that QA/QC is applied to both the geotechnical information and specifically to the LiDAR information. And part of that QA/QC process is relating the LiDAR point cloud, shown as all these pretty colors and points over on the right, to the actual field conditions. So we can see that there are high-rise buildings represented in the LiDAR. Those are real. We can see vegetation. That's real. And there's ground below the vegetation. We have to go into the vegetation and under the vegetation to actually get validation of what ground features are being represented and remotely sensed by the LiDAR data. And it's good to look at it from multiple directions. So here we see a profile of ground return points. Those have been filtered out using an automatic algorithm, and that automatic algorithm then spits out all other points as non-ground points. So these haven't been further classified yet as a building, as vegetation. And it's important that if it's found that there is the algorithm is not working for getting the ground filtering that you need, then you need to rerun the algorithm, and it may be necessary to do manual adjustments as well. And so, again, taking three different perspectives at the same time, simultaneously analyzing the data is very important, because we can see anomalies in the data. We can see areas where the algorithms aren't working properly. Also a good idea to look at what effect the vegetation is actually having on the LiDAR's ability to actually create a ground model or a digital elevation model. So here we can see in red areas, those are areas of very dense vegetation where the LiDAR is not easily able to penetrate to the ground. And then the green areas are areas where probably have almost no vegetation, and that's true for this area. This area is commonly affected by wildfire. So there's just a little bit of grassy vegetation that comes back seasonally. There's a common misconception in creating a digital elevation model that all digital elevation models are created equally or from the same process. This is an example of 7 different approaches to creating a unique digital elevation model. These are all readily available using ArcGIS and QGIS, OpenGIS software. And just in comparing some of these features, you can see that these algorithms generate very different geometries in the terrain, different surface roughnesses, and they resolve hard features or soft features differently. So it's very important that you know how these approaches work and that you apply them in a meaningful manner towards the actual purpose that you intend to apply the digital elevation model. If you're just going to apply the DEM for visualization, there's a certain type of DEM to use. That is not the right kind of DEM to use for surface hydrological modeling, and the surface hydrological model may not be the right type of model to use for all types of slope stability modeling. So it's important to understand the various disciplines and information that go into deriving a digital elevation model. Here is what I would consider a good digital elevation model for geomorphological mapping. So this essentially resolves the landforms and ground features in a pretty realistic manner. All of this northwest-southeast-oriented lineation across the landscape are old agricultural terraces that are now completely reforested and covered in subtropical jungle. So now diving more deeply into the automated mapping and integrated GIS modeling techniques for the regional approach, if we look at this 7 square miles of terrain in West Lantau, this is an area that had 2,400 shallow landslides occurring in 2008. This area was manually mapped. So this map was drawn by hand from aerial photograph interpretation, geomorphological mapping, and then a hazard assessment, and then that has been digitized by hand into GIS. So this was not modeled based on LiDAR, although it is being displayed for visualization purposes on a LiDAR digital elevation model. This map took about 8 months, 6 experts supported by a team of 20 technical professionals, and about $700,000 to $800,000 US spent by the Hong Kong government in order to get this map put together. I propose a much cheaper, faster approach for generating a regional hazard assessment like this. And in the subsequent slide, we'll zoom in on that area. So this is the zoomed-in area. It looks like the hillshades here are the image quality is a little degraded, so I do apologize for that. But this is a DEM or hillshade representing a DEM for the same area of terrain between these two images. In red, we can see areas that have been manually identified through aerial photograph interpretation and then manually mapped as being prone to channelized debris flows, and then a little bit less severe hazard from open hill slope, debris avalanches, and debris slides, and then relatively minimal hazards from higher up in the terrain, and relatively no hazards from the ridge lines. But with using a DEM and an algorithm or two, we can automatically map out very closely those similar landforms. And you can see in black lines, the line work from this image is overlaid on the automatically generated landform map. And we can see some good correspondence between areas where channelized debris flows may occur and also areas where maybe the manual mapping and the judgment that went into drawing those lines was not agreeable with the model environment for various reasons. And then run a slope stability model, and that basically tells us the probability of failure is highest in red, and in blue is relatively lower, and then somewhere in between in other colors. Integrating those two maps, we can essentially derive a simulated landslide hazard map. And then, so I'll make a comparison of those in the next slide, but just briefly, Dr. Bill Hanneberg has developed the map-based probabilistic infinite slope analysis software. It uses a factor of safety equation, and that factor of safety is then distributed across any range of statistical distributions that you like in order to model the probabilities of failure in each location in the site. It's quite a flexible model. This model is particularly more useful than ShowStab or SynMap because it also uses static and dynamic modeling, so you can actually put numeric displacements in here if you want to model coseismic landslides. So all these approaches are applicable to California. We can do static and coseismic landslide modeling. You get a result like this. This is a map of the probabilities of failure, and this map has been integrated with the automated mapping and the geotechnical parameters database in order to get a site-specific map like this. So going back to looking at the workflow for the area that we were previously looking at in plan, this is a 3D view of a digital elevation model, the manually drawn hazard map overlaid on that. All those little green dots are shallow landslides that have occurred in the last 50 years or so. And then we'll pull away the colors, just leave the line work. So this is the manually drawn line work, and then we'll make a comparison to a completely computer-generated output. So we can see there are similarities and differences in some of these areas. We can see very close correspondence in other areas. And then things get a little muddled down in these areas, and that relates to the types of judgments that were made by the engineering geologists in determining whether a debris fan relates to hazards or not. The problem with these debris fans is that they've been generated over about 60 million years, and they represent 60 million years of history. So using them as a proxy for modern landslide hazards is maybe not the way to go. Maybe using just the terrain itself, which is represented in the LiDAR digital elevation model, might be a way of reducing some of those judgments that tend to lead us into areas of poor professional judgment. So looking again at that same area in plan view, we can see that there is a major break in slope across this part of the terrain. The geologists that did this assessment decided to lump those two areas of terrain together as far as landslide hazards, but the model is telling us something different. There's about an 80% difference in the probabilities between this part of the terrain and this part of the terrain. That is significant, and in my view, being friends with these guys and having discussions with them about it, they tended to agree that maybe their judgment was a little too short-sighted in deciding to lump these two elements together, and that probably 5 hazard zones instead of 4 hazard zones would have been a more appropriate judgment. So this demonstrates, in retrospect, the use of this sort of model for challenging and checking our geoscience or engineering-based judgments. So now let's look a little bit more at the site-specific approach. It's essentially using the same models, but we do analyze in more detail the laboratory testing information in order to derive things like the cohesion and the angle of internal friction. In this map on the right, we can see the automatically generated landforms. There are 4 landform classes in this particular model suite that we use. So we've derived areas where channelized debris flows can occur along drainage lines, open hill slopes, more steeply dipping rounded slopes, and also areas of rock outcrop. And when we compare that automated output to a map drawn by friends at the consulting firm Arup, which is a British-based consulting firm, we can see that there are some similarities and differences. Obviously, the map on the left is much prettier, and that's because it's not just a clunky raw output from a GIS model. Of course, you can pass some cartography across these sorts of things to make them really pretty maps like this. But essentially, we are seeing the main concepts conveyed by these two maps are similar. We have these drainage lines or mountainous streams that can be affected by channelized debris flow. We can see a variety of different types of terrain up in this area. Now, it's interesting, they decided not to map this as a different landform, or classify it as a different landform, rather. They did geomorphologically map it, but our classification puts it in a different class than theirs does. So after you go through the automated mapping process, integrating the geotechnical parameters into the automatically generated terrain unit map, integrate that with a LiDAR DEM, and then pass it through the slope stability model, you extract the probabilities of failure. And so red shows probabilities of failure above 0.75, and blue shows probabilities of failure below 0.25. And then areas that are blanked out, those are areas of rock outcrop. This model deals with soils. It does not deal with rock mechanics. We would have to extend the use of the model for integrating with rock mechanics. Rock and soil mechanics are different, as you all know, and so it would probably behoove us to look at rock hazards like rockfall and soil shallow landslide hazards as being different types of modeling approaches. But in order to get that sort of output, you have to do some sort of model calibration. It's always best to calibrate models when you know where the landslides have occurred. Many of these small sites have not had recent landslides or landslides that can be studied or resolved in good detail from aerial photographs or from field reconnaissance. So we have taken a sensitivity analysis approach to testing the sensitivity of this model to the pore water pressure coefficient, which is one of the parameters in the PISA-M slope stability model. And then after extracting those values and analyzing them statistically and graphically, we arrive at our preferred platform for delivering the model results. And so we see here 5 different sites of various plan areas and 3D areas as well. And we can see that using the same modeling approach to mapping out the landforms and classifying them using the same classification system, and then integrating those across the same LiDAR data set, implementing those data in the same slope stability model, we then have a repeatable, reproducible result where the results are benchmarked. There's a baseline to compare each of these, and we can see that there are distinct visual differences between each of these study areas. This gives us the ability to rank these areas for various purposes, whether it's for risk management or whether it's for budgeting out where you're going to need to focus your resources for maintaining your debris-resisting barriers. There are multiple uses of this type of approach. In order to then analyze catchment by catchment, we can use some automated watershed delineation algorithms, and this has allowed us to basically divvy up each of these smaller catchments so that we can see this one's affected by channelized debris hazards, this one's affected by channelized debris flow hazards. These smaller ones are not. Those are affected by small, shallow landslide hazards. This is important because this allows us to extract the probabilities of failure within this catchment, to compare them to this catchment, to make a decision about which one's more hazardous, where's the risk going to be higher. And then we can also further analyze by breaking down the various types of terrain units in here and then extract the probabilities of failure for various types of terrain to take a geomorphological mixed with an engineering type approach to assessing the hazards. So there's quite a lot of versatility in here. And then once you divvy up the terrain and divide those watersheds, then you can extract those probabilities. And this is just a graphical way of looking at those various probabilities between these sites. So these probabilities are broken up between these 5 sites, and then they are compared by hazard type. And you can see quite clearly the magnitude of these probabilities drops out from this analysis very quickly. These models can be deployed quickly and cheaply, relatively cheaply, depending on the size and complexity of the study area and availability of the data. It's really important at the end of any modeling exercise to try to bring it back to reality. Until we have landslides in any of these study areas or high-intensity rainfall that does or does not result in landslides, it'll be difficult for us to actually assess the effectiveness of this modeling approach. However, we can compare to previous studies. This one is a landslide hazard map generated at a 1 to 20,000 scale. This modeling is a 1 to 1,000 scale modeling, so there's a big difference in the scale of these approaches. This one's all aerial photograph interpretation-based and judgment-based. You can see that, yeah, generally they capture that this is a high hazard zone, and we see some high hazards here and relatively lower hazards. It's a comparison across an order of magnitude and mapping scale. Going into a 1 to 5,000 scale study compared to 1 in 1,000, we can see some similarities and differences between these as well, but generally there is good agreement, but of course much more detail in this approach. And there's quantitative information here. This has been generated in a GIS, but it's all based on aerial photograph interpretation, and it's a weighted sum type of approach, so it's not really an analytical approach. ARIP attempted to do more of a statistical approach to modeling these hazards, but you can see, and they agreed, and they put it forward in their assessment that this model is not really useful. It's not really giving any useful information, but it did nicely pick out some areas where previous landslides had occurred. Of course, this model also finds a very similar thing and tells us a lot more about the surrounding terrain. They didn't consider that the reliability of this model was very good in the spaces where it didn't agree with the landslides, which is a bit of a convenient outcome. Thank you very much for your time. I'd like to thank all my colleagues, former colleagues at Fugro and friends at AECOM, ARIP, and GeoRisk Solutions. Thanks to the Hong Kong government and to my team that helped me to envision these and innovate these solutions for Hong Kong, and looking forward to deploying them in California as well. Thank you.
All right. Thank you, Bob. Man, that was a lot.
I'm sure it was.
They kept you busy over there, huh?
Very busy.
Okay, I'm looking at my board. I don't have any questions, so if you have any questions for Bob, now's the time to send them. So you said this LiDAR has applications in California. Have they been using it to look at burn areas? Do you know? Or
I've only been back in the industry in California for 2 months. I am aware that there is a lot of activity surrounding wildfire and tree mortality. Remote sensing approaches are definitely applicable to it. I worked in Yosemite and was kind of associated with some of the fire management activities there. So in using that background and looking more deeply, I do definitely see some applications of integrating LiDAR with other spectral types of remote sensing approaches and hyperspectral approaches to mapping out some more of these environmental issues that relate to slope stability issues. So I do see some capacity to integrate for instance, bark and bear wildfire maps. So those are soil burn severity maps that are generated by the U.S. Forest Service, USGS, and National Park Service in collaboration. So those products are publicly available, and I think that those could be implemented in this sort of GIS modeling environment to kind of tie the slope stability geotechnics back more towards the issues that soils face when they're after burn.
Right, because one of the issues we have here, I mean, we've been in a drought here, and there's
Right.
been several wildfires over the last couple of years. And I think a lot of people are kind of like, oh no, when the rains do come, are we like really going to be in for a bad time with those burn areas?
Well, I'm not the person to ask that. I'm sure that Jerome will fill us in on the wildfire issues.
Yeah, I'm kind of like doing a bridge here. Okay.
Thank
All
you.
right. Well, we don't have any questions, so thanks a lot, Bob. If you do have questions for Bob, you can submit them as you think of them, and we'll get them to him. And, again, include your email so we can email the response back to you. Okay, we're going to take a quick 5-minute break so people can, go to the bathroom or get a snack or coffee, whatever they need. But it is going to be 5. It's not going to be 10 or 15. So I've got 11:01 now, so we'll be back at 11:06, and we'll speak with Jerome then. Okay, so see you guys in 5 minutes.
This meeting is now being recorded.
Thank you. Are from lightning strikes, and if you ever saw the results from a single storm from the National Detection System in North America, you would think that we're lucky that we don't have more wildfires from lightning than we do. Only a very small number actually result in an actual fire. But notice I did say natural ignition sources because there is the human factor. There are lots of places in the world where we have intentional fires for agricultural purposes, as we see in this photo, to either remove the last year's crop or to clear natural vegetation to start new fields. And of course, under the intentional, we also have arsonists because we know there are people who are as likely to start a fire on purpose in the forest as there are those who would do it to old warehouses in an urban environment. Now, also, there are plenty of accidental ways, which might be it's sort of interesting in the fact that it seems like there are almost as many different ways to do that accidentally and start a fire as there are people. We have a propensity for using cutting torches and other things that produce sparks that we use even when we know we shouldn't be. In wildland areas that we think of as being pristine, there are plenty of power lines that run through the area where trees can grow up among the lines and arc and cause a fire, or transformers can fail, as we see here. This one is sort of unique. These folks had just left the El Portal exit from Yosemite and were going down Merced Canyon, and I'm sure that they had a wonderful time in Yosemite and were maybe perhaps going to a park over on the coast, but they suddenly looked behind and realized their motorhome had caught fire. And having separated themselves from the motorhome and notifying folks that there was this fire, by the time the trucks got there, it was running up both sides of the canyon from this source and was a multi-day, multi-thousand acres of wildfire cause. So lots of different ways in which we can end up with a wildfire being created by human ignition sources as well. Now, when we think about fighting wildland fires, these may be the kinds of image that comes to mind, and these are very important tools for actually fighting wildfires, retardant drops, water drops, and such, but these don't actually put out the fire. These are the folks that put out the fire because they're controlling the only thing we have any control over. Because the fire heat source has already happened and the oxygen is in the air, so the best you can do is to essentially create a barrier of no fuel by hand digging, often bulldozers we'd like, but the terrain is usually requiring that it be done by hand. And where we can, we also increase the width of that barrier of no fuel by burning out the adjacent area. So this is containing the fire within this fire line of no fuel is how we really bring the fire to its knees and get it finally put out. So that's the way we find ourselves dealing with fires, and here's the sort of forecast we find ourselves having to deal with in the western United States, and all my remarks from here are strictly on the western United States. We seem to have an increasing wildfire frequency and magnitude, numbers and size. So if we look at numbers of fires, we can see the trend going up through this period. If we look in just terms of total acres being burned from all the way back to 1915 to 2010, and the truth is 2015 was a record with 11.1 million acres of state, private, and federal lands going up in flames in that year. We would have to make this graph even bigger. So why are we having this? And why is this forecast continuing to be on the rise currently? Well, back in 1910, we had the Great Fire of Idaho and Montana, which was just one of a number of large ones in the West, and it generated, sort of like the last straw, generated a call for fighting fires and started the policy that was instituted then of trying to suppress every fire that started here in the West. And most of that fell on the shoulders of the Forest Service, but also other land management entities like the Park Service and the Bureau of Land Management. Well, we can see that policy, as they got better and better and got the resources into hand on this thing, brought us into a low period of wildfire. But somewhere right about in here, it was the ecological studies that were coming in more and more showed that fire is natural to most of the Western ecosystems. In other words, a little fire is not a bad thing. In fact, it's a desirable thing for maintaining a healthy ecosystem. So that posed a quandary for what we had been doing, because all that effective work back through here now meant that many of those ecosystems had far more fuel laying around within those ecosystems, than was part of the natural balance. So to stop fighting the fires that were starting in those areas and just let nature take its course would mean that we wouldn't be reinstituting the natural ecosystem. We'd be essentially causing it to be really knocked back and seriously impacted. And then we can see that it was already beginning to happen naturally, but there are other forces going on here. For instance, we also have an expanding population in the West. So that means that we're going to be getting an increase in the human-caused ignitions through the expansion of the wildland-urban interface. And what we mean by the wildland-urban interface is sort of shown in this photo of Boulder, Colorado, where up here this wildland is the Roosevelt-Arapahoe National Forest in the foothills area. Down here is Boulder, Colorado, University of Colorado right there. And here's our wildland-urban interface, which is not really a sharp line, but more of a zone, because we can see a little wildland over here on the urban side, and we can see a little bit of urban developing on the wildland side. So that's the situation. As we have population growth, this wildland-urban interface expands, and consequently we have more effect as far as potential ignition of fires by the population, mostly accidentally. And that population growth in the western U.S., if we look from 1900 to 1990, we can see that it's expanded by 1,500%, as opposed to what during that same period the entire U.S. was 225%. And we can also see, looking at the map and knowing the terrain, that when we look at the places where we've had the most growth, we know a lot of those are right next to major wildland areas, whether it's the Wasatch Front or the Colorado Front Range or down here in Southern California on the mountain ranges in proximity to it. So we have a growing wildland-urban interface, which means we've got plenty of opportunity for fires to be started. So that's one of the factors that's obviously playing in this. We also have a limitation to firefighting techniques by this expansion of wildland-urban interface, because if you have a natural landscape and you get a lightning fire started in this particular area, you have, a lot of options for very quickly containing it while it's in a much smaller size. But if you have subdivisions and individual homes and other things in that area, then that means that you're going to be trying to protect them, and you're liable to end up having to encompass a much larger area and be constrained in trying to keep it small in this kind of situation. So that sort of favors having more larger fires. Also, that reintroduction of fire into the ecosystem by controlled burns is sometimes hampered by this, because people naturally are concerned that controlled fire might get away from the firefighters, even though they go through a lot of effort to avoid that. And people are more prone, as we all are, to worry about the risk that you perceive as being immediate than the one that might be out in the future that they would be protected from by the ecosystem returning to normal. So there's one other variable. That's all the sort of the people policy of the effect on getting larger fires. But we also have a climatic variability going on that's a little outside the normal variability that we can record in old tree rings and such around the West. And basically, this was first shown by Westerling and others in 2006, and it basically found that we've got a reduced winter precipitation, earlier spring snow melt going on, and this correlates with having an increase in the larger fires starting about mid-1980s as an issue. And so this shift means that we've got a climatic factor leading to us having longer fire seasons, because it dries out sooner and it stays dried out longer, and therefore it's more receptive to whatever ignition source might occur, leading to having these fires. So all of these things are conspiring together to increase the amount of burned area we have within the western United States. Now this is where we get into the effect on the landscape that I'm most concerned about. And I would point out that the red here that we see in this map in the western U.S. Is the land that is managed by these entities of the federal government. And one thing that happens with wildfires is when you have a wildfire of any size, 600 acres or more, burned area emergency response teams are initiated to go and be at the fire as it's becoming contained before the fire is actually out. And their role is to assess and focus on the risk from storm-induced hazards. In other words, what's going to happen when the storms come. They're specifically looking at the effect of how the fire has affected the landscape and what potential threats to life and property on federal lands might that create. Obviously, they're going to identify where lands adjacent to those federally managed lands are threatened, but because you're not allowed to spend taxpayers' money just everywhere, that has to be on the federal land, but you can share that information because there are other people who have some responsibility. And this sort of shows that this area is a little fire called the Early Fire. This is on the Stanislaus National Forest and the Tuolumne River drainage. What we're looking at here is a parking lot for a popular trail on Forest Service land, so the trail was closed. The parking lot was closed. A sign was put up to explain why, due to potential threats during storms from where the burned areas are. We don't want people at risk. And also, you can see there's a penstock coming down, bringing water from Hetch Hetchy Reservoir into this powerhouse in this area is known as early intake. So this is under a federal regulatory license to the city and county of San Francisco for power generation. So the information of what might be coming down this hill into their facilities was shared with them, and they were, this component right here, were able to take some measures to protect their operations. What many people are not aware is that the BEAR process is a rapid assessment with a report required within 10 days of fire containment to be able to essentially release money for a fund, because the BEAR report will be defining where there is an emergency created by the burn, what that emergency is, the nature of it, what might be done to mitigate it, and of course the cost of that mitigation. So as a geologist, for looking at post-wildfire geohydrologic hazards, you've got three biggies: debris flows, rockfall, and flash floods. Now, when I've been been on BEAR teams in the years just before I retired, we realized that our hydrologists on the team would come with these really great programs on their computers for modeling the increased water flow, and that had a lot to do with identifying where the flash floods would be. And so we decided we'd just let them handle that, and it was we'd focus on the debris flows and rock falls, because that was enough to get done as it is. Let's look first at rockfall hazard and how we are going to assess where things have been changed by the fire to create that impact to a greater extent. And we're going to look at a video here that shows a fire in progress in Northern California. There's no crews up on the slope. What we have is the Smith River creating a wonderful barrier to the fire moving beyond this point to behind the observer. But you'll see there's things falling down. You can see some of the burning going on. We've got all of the smoke coming up. But we also can see a lot of dust being generated on the slope. And that's the interesting thing that we're looking at here. It's due to the fire. And if we look down here, we see these splashes, and these are not salmon rising to the fly. These are larger rocks, because all of this is sand, silt, and bigger rock chunks moving down toward this particular, down the slope. You can see we have soil, but this is typical of the situation we have. I'm sorry, I moved that ahead too fast there, and we'll have to repeat a little bit of that if you don't mind. This is all without a storm, just naturally due to the removal of covering vegetation, the root masses of fine plants on the understory, the removal of down woody material that has been laying on the slopes, and therefore once all of that is removed, we start to have this material moving down slope. In Southern California, a term for this kind of action was identified, and it's referred to as dry ravel, because you don't have to have a storm flow to get this all going. Now, it's fine if you've got a river like the Smith River catching all of this stuff down at the bottom of the slope. Not necessarily the best thing for water quality, but it's going to be a transient effect. But if across the mid-slope or at the bottom of the slope you find yourself with a road, we're going to see in just a second here that what you then have is all of that stuff coming down and accumulating in debris cones on the road, which can grow to being half the width of some of these smaller roads. And I'm particularly interested as a bear geologist in these larger rock fragments that we have from this. And here's this representation of dry ravel and how all of this stuff moves down slope. And I have to say that Dr. Lamb at Caltech, when we had the 2006 station fire in the St. Gabriel's next to Los Angeles, rightly realized he had a natural laboratory of some value right in his backyard. So he started sending up students to sort of quantify the degree to which material was kept behind vegetation so that you might even be able to make a better estimate of how much dry ravel might be coming down as a whole. Now, as I said, I'm sort of interested much more from a hazard standpoint in where we have lots of small rocks that either are going to block the road or they're going to damage tires and stuff like that is a detriment. And particularly to bigger rocks or ones that might be moving. Here's one of the bigger ones with my hard hat next to it, because you can get damage to vehicles. People can be surprised by them and react badly and get into accidents, get themselves hurt. And it isn't good if you have an actual paved surface either. As far as the hazard to people, this one in Idaho sort of shows this. The folks who were driving this particular vehicle had been parked over here and were making an assessment. They were fire guys assessing the degree to which there had been damage to a work center. And they heard this thumping and bumping coming right down this slope behind them. And when the rock, it was a boulder, and here's half of it, because this is where it struck right at the road, and half of it bounded across and rolled out into the area past that, as you can see. They pulled their truck up here to show, since they were just about to leave, that if they had not, if the timing had been just slightly different, that rock flying off would have hit the side of their truck and could very well have injured somebody. So how do we decide in an environment where we have lots of steep slopes and we have lots of natural rockfall already going on, how do we decide where there are areas that the fire has increased that emergency potential, creating an emergency? Well, the only thing I could think to do was to essentially start looking at road segments during my burned area emergency response surveys and collecting data like how recently how many days had it been since the fire passed over that slope, what was the biggest rock I already had on the road, what was the rock type, what was the slope percentage steepness that we had above the road where those rocks were coming from, and also whether there was what was the soil burn severity of that particular slope. How had the fire affected the vegetation, for example? Soil burn severity is something that's now routinely done for wildfires. This is where they use satellite imagery to compare pre-fire and post-fire images and look at the reflectance difference to identify where the vegetation has been completely burned, partly burned, or just slightly burned, or not burned at all. And that's what we see partly represented here. These polygons are then studied by the soil scientists on the Bear team to look at the effect on soil, whether the heat of the fire had caused a hydrophobic layer to develop within the soil. This is not unlike getting soot on the inside of your wood-burning chimney for your fireplace, where the incompletely burned organic gases that the fire is creating are driven into the pore spaces, the air pore spaces in the soil. They cool, they form this layer that essentially means that the infiltration of the soil is going to be somewhat impaired compared to what it was before the fire, and will naturally break down over time. So they modify the boundaries of these soil burn severity units, and we found that high and moderate was typically associated with where I was finding these rock falls. So how do we use this? here we are at the Rim Fire in 2013 with 748 kilometers of road within the burn perimeter that we have to assess for potential rockfall hazard because very little of anything was flat slopes in that area. So you see an area like that, and you know that granular material came down after the fire, but how much of these larger chunks had come down as a result of that fire? So basically, to identify where we were having an emergency due to the rockfall, we went to the GIS people on the Bear team and had them give us a map in which they identified where we had these two conditions, 39% slopes or greater or moderate or high soil burn severity immediately above the roads. Well, that meant that we only had about 78 kilometers worth of road that had these conditions, i.e. the only parts of the fire where the road system within the fire that was likely to have had an emergency situation created. So we went forward with reviewing those particular areas with a protocol that said, okay, we're going to identify an increased rockfall hazard due to the fire in any place where we're currently finding a rock or more rocks that are a third of a meter in diameter or concentrations of 10 or more rocks of a smaller dimension that somebody wasn't going to be just able to drive around. So when you looked at all of those, you found there were only 10 segments within the Rim Fire where we had these kind of conditions, and it turned out it was only 15% of the GIS identified road length, about a total of 10 kilometers in 10 segments were involved. Now that was where we had some confidence that this is where the emergency rockfall hazard existed due to the fire, and some mitigation could be identified for those segments that was appropriate for the situation at each one of them. Now, debris flows. Debris flows are a little more mature study and approach under wildfires. We know that they cause problems here in Santa Quin, Utah, caused a lot of physical damage, a lot of insurance claims, a lot of work, a lot of heartache for the people who lived in this subdivision. Here at Waterman Canyon, you see a foundation right here for a one-story structure. You can see the debris flow deposit around it because it came down through, tore that structure completely off the foundation, reduced it to kindling as it continued down the canyon, and also killed the 14 people that were inside of it at the time taking shelter. So seasonal rainfall comes, debris flows may occur when we have burned areas. What makes these debris flows so hazardous? Well, when you've got essentially a mass that is flowing in a viscous manner because it is a slurry, not unlike the character of cement coming out of a ready-mix truck, and even better, it has a bouldery front because it entrains large masses of rock in the front of that and moves down through a channel or a low area down the slope. It moves relatively rapidly. This is one in Merced Canyon that in the Sierras we have them going 12 to 15 miles an hour. Doesn't sound like much, but if you think of that hitting the side of your vehicle or a structure, you can see that's pretty destructive potential. And they also have the habit of traveling well beyond the perimeter of the fire itself. So areas that were otherwise safe due to the fire are now threatened by this post-fire effect. They can move 2 and 3 miles. So here's what it looks like. This is from the Paiute fire. Thunderstorms started over top of the burn while it was in progress and being fought. The Kern County put their helicopter up to catch the flash flood that was forecasted, and instead found a debris flow coming down Erskine Canyon heading for the community of Lake Isabella. You can see the internal strength of a debris flow that is due to that viscous flow manner. It looks more like like a lava flow, which is enhanced by the amount of black ash involved in this particular debris flow we see here. It'll be coming across these low water fords that they have in this road to allow the stream and the spring melt to go across. And now watch, it's going to look up and you're going to see this is where the debris flow is coming from. So this debris flow has traveled several miles well beyond the fire perimeter at this particular point. Also, it's picking up some really nice battering rams as it then drains some of these trees to carry it off. So this is the kind of situation that we're trying to deal with. Now, fortunately, Lake Isabella had the foresight to not build right up to the edge of their channel, so the people were able to take pictures as it went by, and it made very little damage to the town itself. Now, post-fire debris flows. When I was first getting into this particular assessment was 1987 with the Stanislaus Complex fire, and so I'm expecting that I'm going to be dealing with the things I normally deal with in the Sierras of infiltration-induced debris flows. This is the typical thing where you have a lot of rain coming down, an intense storm, a small bit of material gets generated, slides into the stream. Between being pretty wet itself and then the additional water, it begins to disaggregate, become a debris flow, race down until the channel is either less confining or the slope gets gentler and then deposits here as a fan further down. So my approach for a bear team was to then look on the slope where we've had very intense burn activity and most of the vegetation had been removed, and to look for evidence that we had infiltration induced debris flows, little scars up here in the upper part of the watershed, maybe some parts of deposits of past debris flows here. Did I have a fan down below? And what kind of structures or facilities were at risk that I would identify a potential debris flow hazard from this particular approach? And that was how I proceeded, and it was somewhat discouraging to find out that approach was completely wrong, because post-fire debris flows are not infiltration-induced. They're generated through runoff-dominated erosion, as Dr. Susan Cannon showed in 2001 when she published the results of her PhD thesis. And so basically, we don't have a distinct identifiable landslide source where our post-fire debris flows start. We're liable to see rills, actually, across the landscape. And you might notice in this debris flow that the farther you come down, the more distinct the track of the debris flow is, and that's because it turns out the great majority of material that finally comes out the mouth of the channel or down where it finally deposits is eroded from the channel network here. In fact, some of it is a lot of that dry gravel that's moved down the slope to the ephemeral or intermittent channel that might exist there. A lot of this aspect of how much material comes from the channel network came from the study by Paul Santee and others in 2008. And here's a guy for scale just to show you in this cross-section how much material came out of just that part of that slope as a debris flow went through down the slope. So that put a whole different light on assessing post-fire debris flows. Fortunately, Dr. Cannon and her cohorts at the U.S. Geological Survey then went forward and continued their research to give us empirically derived models to produce maps for watersheds as small as 0.2 square kilometers. And here's the rim fire with a map showing where the probability of debris flows would be. And they also could produce a map that showed the expected volume, the probability of different volumes. And this was all calculated for a particular design storm event. Well, then if you put the probability of occurrence and the probability of larger or smaller volumes together, then you come out with a hazard map of debris flow hazard on that burned watershed. And you can focus your on-the-ground studies to those watersheds that have the most potential of creating that hazard for any values at risk that might be downstream, whether it's a hydroelectric facility or someone's structure or a road, any of those kinds of things. And that's the current approach that's largely used by the BEAR team to assess debris flow hazard. Now, one question is how long does this hazard last? Well, the study of 75 debris flow responses within burned areas throughout the western U.S. found that 85% of them occurred within the first 12 months after the wildfire, and 71% of those took place within the first 6 months. Okay, so consequently, this means we don't have much time between the end of the fire and the start of the rains, sometimes only weeks, to mitigate that particular threat. Now, you still can have that persist beyond the first year, as this debris flow outside of Independence, California showed, which occurred 2 years after the Inyo complex fire up here, and closed Highway 395 and wiped out the Mount Whitney fish hatchery from being able to effectively continue operating. So we're not out of the woods until at least a couple of years after the wildfire, but then it does cease. Now, this means with this system of having these identified hazard watersheds, we might be able to, if we can move fast enough, put in physical mitigation measures. Maybe you live in Los Angeles basin area and a debris flow basin is already there thanks to the public works people concerned about infiltration type debris flows in the past from storms. Or sometimes the best we can do is have early warning systems to remove people from the risk of being in an unsafe place from a debris flow. And because they've gotten very good at developing evacuation plans and working this out with the folks in the Weather Service, so they issue debris flow watches and warnings just like we do for flash flooding. But there's always the problem of warning fatigue, because people voluntarily going to a shelter, if it's the second or third time in the same winter, you get this warning fatigue, which essentially manifests itself, with like, imagine you're in a living room with Ethel and Harry, and Ethel turns to Harry and says, "Oh, they just called another evacuation. I didn't get a bit of sleep when we were on that hard cot at that evacuation center last time, and I don't want to go to your sister's again. So why don't we just stay here, and probably nothing will happen. Nothing happened the other times." Well, the reality is maybe Ethel's right. Maybe nothing will happen just like before, or maybe they'll have something that look like Santaquin that have a lot of cleaning up to do, or maybe they'll have Waterman Canyon. So that's the issue that unfortunately the emergency response people have to address, and it's why we worry a lot about getting it right as far as identifying where that hazard is greatest. We are going to have to deal with this for the foreseeable future, because we're going to have bigger and more frequent wildfires. At least we have a better understanding of why and where we have them that lets us do a more robust risk assessment. And so hopefully emergency response can utilize physical measures and early warning systems to better protect life and property. I would point out this web address right here. If you go there and find my smiling face, there's a link right in the middle that if you click will bring up a PDF which has the citation for all the papers that were used in this presentation as reference, and also some other related papers that are pretty valuable for this particular topic. Thank you very much.
All right. Thank you, Jerry. Okay, does anyone have any questions? I'm looking at the Q&A, and I'm not seeing any. And I'm also looking
Everybody
at my...
went to lunch.
What's that?
Everybody went to lunch. Smart
Oh,
people.
I don't know. We've still got everybody still logged in. We haven't lost any people. So if you have any questions, send them now. In the meantime, I want to thank Jerry for his presentation. Really appreciated it. Let's see. We have
one.
Oh, do we have one?
I see one under public chat.
Aha.
Instead of Q&A. Basically, it says, is debris flow risk abatement with time due to the realization of debris during the ensuing time frame or due to pedogenic and vegetation processes that stabilize soil? I think basically over time, the change, the storm effect on hydrophobic soil, the revegetation process that goes on from seeds that are in the soil sprouting from the vegetation, stabilizing the soil tends to reduce the potential for these runoff-dominated generated debris flows, and it would be nice to have a better idea of how rapidly that happens. The best we have is this sort of notion of 2 or 3 years after the fire, but that doesn't take into account whether you also are having a drought now or not. So there's a lot of potential need for more research in that particular area for sure, but does seem to be due to the soil vegetation processes.
Okay, and we have another one. Looks like Val. It says CGS produced a document in 2014 on pre-wildfire studies for pre-wildfire mitigation. Are you aware that these techniques are being? Are you aware if these techniques are being applied by wildfire managers? Oh, and it says Bob.
Yeah, I have not. That particular document, I'm not sure I have, but we have a similar one in the Forest Service that put all these together just about 3 years ago. Let's see. I've got to remember when I actually left. That sort of, so it'd be about 2012, I think it was. That's where we get our techniques from, and we follow our normal procedures. I'll be happy to look that up because that might be useful to add to my landslide course when I'm teaching it.
Okay, do we have any more questions? Okay, this is from Ronna Bowers. Do you have any?
Right.
Do you have any thoughts on the? Oh, go ahead.
I was going to say that basically when it comes to magnitude or intensity of threshold storm events that typically trigger debris flows, that's part of it goes back to that design storm that seems that's used in calculating the model that the USGS has, and they're working on trying to develop more of an objective threshold that can be used for areas, and that's an area of active research that they're making a great deal of progress on. Look for papers authored by Dennis Staley and others from the U.S. Geological Survey. There's one out by he and Jason Keene on objective thresholds for Southern California, and I know there's another one that's in press that Dennis has put together. So that's the direction that's going to get even more deeply into what are appropriate thresholds.
Okay. Well, thank you. All right. Well, I think this concludes our. Let me scan my control panel here once more. I think that this concludes our presentations for today. I want to thank everybody for participating. Thank you for the questions. If you think of anything later, you can email me, and I'll get the questions over to the presenters, and we'll get them answered for you. if we are planning on having our next symposium, I think we're going to try in the spring. The date is not set, but we'll be shooting for April or May. And now I'll repeat the goal of the Geosymposium. Our vision includes promoting interagency cooperation and collaboration. And so if you have any ideas on how we can improve the Geology Symposium or increase cooperation between different state agencies and how geologists are using their data, we would love to hear them. And if you have any ideas for future topics, or if you know someone who is who is doing some interesting work and would like to make a presentation, then by all means get in touch with me. The best way to contact me and get your ideas to the Geology Symposium Committee is to send me an email at jniginis@dtsc.ca.gov. That's J, N like in Nancy, AGINIS @dtsc.ca.gov. Now, if you'd like to help out and be a part of the Geology Symposium, you need to definitely get in touch with me. You can join our impressively named Geology Symposium Steering Committee, and you can have all the respect that goes with being such a part of our auspicious organization. But mostly, you'll be on the phone with us, contacting people, making plans, and implementing the webinars, and hopefully come up with some new ideas. So if you have some good ideas, let us know. And as you log out, there will be an opportunity to fill out a survey, and please take a minute or so to do it, as it really, really helps us a lot. We look at all the responses in the surveys, and we found that the ideas people give us are very helpful, and we've used a number of the ideas for improving our geosymposiums. So before we go, the Geology Symposium Committee extends its thanks to our supervisors and managers for supporting us and giving us the time to develop and present the webinars. So with that, we are sending out thank yous to the Management, Department of Water Resources, Caltrans, DTSC, and the water boards. So I think that includes our symposium for today. So thanks again for coming. Now, I guess everyone can go and have a good lunch. So bye-bye.
Thanks, John. Bye now.